Okay, welcome back everyone. Kind of wanted to close out this chapter by highlighting the topic of apparent weight and weightlessness. And as I mentioned in a previous video, even on the space shuttle, astronauts were not weightless. They experienced an acceleration of about 8.9 meters per second squared. And they're only 320 kilometers above the Earth's surface. That's only a couple hundred miles. If you think about this, you could drive a couple hundred miles in a day easily. So they're not that far away from the Earth. But this concept that we have of weightlessness really has to be dispelled. And so here are a couple things to think about. A better concept to think about is that of apparent weight. So apparent weight could be thought of the normal force acting on you. Seems kind of simple, but think about this. If you're flying in a plane and someone pushes you out, you have a parachute, but you don't use it at first. As you're falling, is anything exerting a normal force on you? Well, no. So, do you feel like you weigh anything? Again, no. So your apparent weight would be 0. Okay? So now, imagine that you're standing on the surface of the Earth, and you're standing on a scale, and you're not going anywhere. There's a badly drawn surface of the Earth. Let's make it a bit more level. And so the normal force that acts on you is equal to your actual weight if you're not accelerating. Okay, well, what if you're in an elevator that is accelerating upwards? Let's just say an acceleration of 2. Well, forces acting on you are still normal force and gravity, and like we've done so many times before, we'll apply Newton's second law, say that upwards is positive, so F net equals mass times acceleration, F normal minus F gravity equals your mass times positive 2. So what this tells you, let's say your mass is, just for fun, let's say your mass is 100. Okay, that means that the normal force minus 980, that's your mass, times 9.8, is equal to 200, or the normal force is 1180. The normal force is more, your apparent weight is greater if you're in an elevator that's accelerating upwards. And you know this to be true from personal experience. You've been in an elevator, you feel it start moving, and then all of a sudden you feel a little bit heavier. Okay, so what does this have to do with circular motion? Well, now think about a roller coaster. Okay, so you're at the bottom of a hill, or bottom of a valley rather, in a roller coaster. You have a speed, so you're moving forward, okay? And this is a part of a circle, so because you're undergoing circular motion, you are accelerating this way. And so this situation becomes identical to when you're standing in an elevator. You have a normal force, you have gravity, and the normal force has to be greater than the force of gravity. Because if it wasn't, you couldn't be going in a circle. You wouldn't have an acceleration. Okay, well, a similar thing happens at the top of a hill. In this case, the circle is pointing downwards, or the center of the circle. So that's your centripetal acceleration. And in this case, well, if we look at these two forces, the normal force pushing up and gravity pushing down, what has to be larger? And it looks like it has to be gravity. You have to have a net force pushing downwards on you. So that's why at the top of a hill on a roller coaster, you actually feel less heavy. The normal force has decreased. So this is the link between the normal force and apparent weight. And so I've switched over to a YouTube video that shows a pretty dramatic example of weightlessness and its connection to apparent weights and the normal force. So this is the so-called vomit comet. This is a plane that actually follows a somewhat parabolic trajectory. And so as you can imagine, up near the top of the parabola, as the plane is trying to sort of curve down again and make part of a circle, anyone in the plane is going to experience something very different than when the plane is kind of diving downwards, and that would be kind of the weightlessness portion. So let's watch a little bit, and you can just do a YouTube search for vomit comet. Some of the videos are better than others. So you can see at the bottom, they're showing the different planets they're on. Okay, so you can kind of get a sense of how reduced gravity gives less normal force, and boy, wouldn't it be fun to be on that plane. Maybe we'll figure out some way to do a class field trip, right? Okay, so that's all for this time, and I'll catch you next time.